Good morning, all of you. The previous day we saw Henry's law. There we considered one gas that is dissolved in another solvent. For example, carbon dioxide gas dissolved in water. XB, that is mole fraction of carbon dioxide in that water, is proportional to the pressure of the carbon dioxide in that solution or on that solution. Carbon dioxide gas can be bubbled through this water with a pressure. So the amount of carbon dioxide gas dissolved, that is XB, that is a mole fraction. We are talking the concentration in terms of mole fraction here. This mole fraction is proportional to the pressure of the gas. Here we are considering one gas and other solvent. And we said, according to Henry's law, PB is proportional to XB, or PB is equal to KH into XB, according to Henry's law. Suppose you see this is a liquid in this bottle. If I keep it opened, then this vapor of this liquid will be going up. If I close this, that time also vapors will be coming and some of the vapors will be condensing to form the liquid. Some of the liquid molecules will be going up. At equilibrium, the rate of condensation and rate of vaporization or rate of evaporation here becomes equal. Rate of evaporation becomes equal to rate of condensation. At that time, we say an equilibrium is reached. Here there is only one liquid. Suppose it is a mixture of two volatile liquids. Suppose it is a mixture of two volatile liquids. I am putting another liquid in this. Okay. Suppose these two liquids, see the color got changed. Suppose these two liquids are volatile liquids. So in a closed vessel, the first liquid, that colorless liquid, will evaporate and that colored liquid will also evaporate. So at equilibrium, there is a mixture of vapors, mixture of gases. I told, consider both the liquids as volatile liquids. Volatile means they will be going from liquid state to the vapor state. So above this mixture, there will be two components in the gaseous state, in the vapor phase. That is, the particles of the first liquid and also the particles of the second liquid. Since it is closed, again I can say an equilibrium will be reached. If it is not closed, they will be escaping. So no equilibrium will be reached. If it is closed, see, when the rate of evaporation becomes equal to the rate of condensation, an equilibrium point will be reached. At that time, you can consider a total pressure of the gas above this mixture. P total. P total of this mixture of gases, that is due to what all things? The pressure of the first liquid and also the pressure of the first liquid molecules and also the pressure of the second liquid molecules in the vapor phase. Let PA is the pressure due to the partial pressure due to the component A. Component A is the first liquid. Component B is the second liquid. So P total, what is P total in the vapor phase? In the vapor phase, what all things are there? Component A is there, component B is there. So Above this liquid, there is a P total which is equal to PA plus PB. Pressure due to component A, pressure due to component B. Now you consider this mixture. In this again two components are there, A and B. Here you can consider one XA and XB. Inside this liquid, XA and XB. Above this liquid, there is a P total, PA plus PB, right? In this vapor phase also, you can consider the mole fractions in the vapor phase, that is YA and YB. So what all things? In the vapor phase, YA and YB. In the liquid phase, means in the solution, XA and XB. And here on the top, P total, which is equal to PA plus PB. Now, there is one PA, there is one XA. Another law called Raoults law states that this PA is proportional to XA. Similarly, PB is proportional to XB in the solution. That is, in a mixture of volatile liquids, the partial pressure of each component, PA, is proportional to its mole fraction in the solution. That is, PA is proportional to XA and PB is proportional to XB. XB is the mole fraction of that yellow liquid in this mixture. XA is the mole fraction of that white liquid in this mixture. This mixture is it is a mixture of volatile liquids. So, another law called Raoults law. Raoults law states that similar to Henry's law, there it was only one volatile component. Carbon dioxide is that volatile one. Water is a non-volatile one. There it is. Okay. Here, two components. Both the components are volatile. So, in the vapor phase, the components of both liquids, means the molecules of both liquid will be present. So, according to Raoults law states that the partial pressure of this one component is directly proportional to its mole fraction in the solution. That is, PA is proportional to XA. Similarly, PB is proportional to XB, or PA is equal to P naught A. That there constant, the proportionality constant is P naught A. PA is equal to P naught A XA. PB is equal to P naught B XB, where PA plus PB is equal to P total. So many things are there. And what is the mole fraction of this component A in the vapor phase? YA. In the vapor phase, that is YB. YA plus YB is equal to 1, because sum of the mole fractions of all the components in a system is equal to unity. Similarly, XA plus XB is equal to 1 here in the liquid phase. XA plus XB is equal to 1. Similarly, YA plus YB is equal to 1. So, similar to Henry's law, we can talk about another law called Raoults law also. We will be doing the numericals of Henry's law first, then we will be moving to Raoults law. Question. What concentration of nitrogen? This is based on Henry's law. What concentration of nitrogen should be present in a glass of water at room temperature? Assume a temperature of 25 degrees Celsius and a total pressure of 1 atm. And mole fraction of nitrogen in air is 0.78 kg for nitrogen is equal to 8.42 into 10 to the power minus 7 capital M slash mmHg. We know Henry's law in general form. Henry's law in general form is what? PB is equal to PB is equal to KH into XB. This is a general form. General form. Yeah, common form. Now, in this case, you see KH is equal to PB upon XB. Pressure unit will be in the numerator and concentration unit, whether it is there or not, it will be in the denominator. But you look this KH unit. Concentration above and pressure below. Concentration in the numerator and pressure in the denominator. That means general form is not applicable here. Normally, I told you 99% we apply general form only. But in this particular case, look at this, look at this unit of KH. Concentration in the numerator and pressure in the denominator. But here pressure in the numerator, concentration in the denominator. So this equation is not applicable in this particular question. So we are going to that other form. What is the other form? XB is equal to KH into PB. XB is equal to KH into PB. So I'm changing this equation. Anyway, here I am not writing XB. Okay, let it be XB is equal to KH into PB. Now you see, here there is one unit molarity. That means concentration is taken not in XB. Concentration is taken in terms of molarity. Molarity. So I'll be writing this instead of XB, I'll be writing the concentration. Concentration is equal to KH into PB. What is the question? What concentration? What concentration? What concentration of nitrogen should be? So, which is equal to KH. What is KH? KH is equal to 8.42 into 10 to the power minus 7. And PB, that is the partial pressure of nitrogen. Partial pressure of nitrogen is not directly given. But we learned last year that partial pressure of nitrogen is equal to P total into its YB, which is equal to, what is P total? 1 atm. 1 atm. And what is the mole fraction of nitrogen in A, YB? That is equal to 0.78. So what is the partial pressure? That is 0.78 atmosphere. This value we will be writing here. PB. What is PB? That is 0.78 atmosphere. 0.78 atmosphere. Now, what all things? This atmosphere, this 8.42 into 10 to the power minus 7 molar upon mmHg. So I'll be writing once again, that is 8.42 into 10 to the power minus 7 capital M upon mmHg. mmHg. Here I'll be writing what? Into 0.78. That atmosphere I'm converting into mmHg. Yesterday we learned the conversion factor. So 1 atmosphere, that is 760 mmHg. Now this mmHg will get cancelled. You can multiply this thing and you will be getting the concentration in terms of molarity. Answer is 4.99 into 10 to the power minus 4 molar. This is the concentration. So what concentration of nitrogen should be present in a glass of water at room temperature? Means air is pressing on the top of that glass of water. Air is pressing. In that air, total pressure is what? 1 atm. In that 1 atm, 0.78 atm, that is the partial pressure of nitrogen in that air. So according to that pressure, nitrogen gas will be soluble. Nitrogen will be soluble. So the concentration of the nitrogen gas present in that glass of water will be what? This much molarity. This much molar. Means concentration term can be any. Here it is given molar per mmHg. Concentration is on the top, pressure is down. So we are changing this equation into the other form, not the general form. The amount of nitrogen gas present in the solution is proportional to the partial pressure of the nitrogen gas. Individual pressure is called partial pressure. How much is the pressure of that nitrogen gas? accordingly the concentration of the nitrogen in the solution. Now let's do another numerical. Question. If N2 gas is bubbled through water at 293 Kelvin, how many millimoles of how many millimoles of N2 gas would dissolve in 1 liter of water? 1 liter of water. Assume that N2 exerts N2 exerts a partial pressure of 0.987 bar. KH is KH of N2. KH of N2 at 293 Kelvin. We know that KH value changes with the change in temperature. At this temperature, 293 is 76.48 kilobar. Kilobar. Kilobar means you can convert that into bar. How? That is 76.48 into 1000 bar. Kilo. 1000 bar. Okay, this is the question. If N2 gas is bubbled through water at 293 Kelvin, so N2 gas is bubbled with a pressure. With a pressure only the gas can be bubbled. How many millimoles of N2 gas? So N2 gas is bubbled through this water with a pressure. So according to the pressure, this N2 gas is soluble. So what is the concentration? How many millimoles of N2 gas would dissolve in 1 liter of water? 1 liter of water. Assume that these things are given. Assume that N2 exerts a partial pressure, that is Pn2. So common form, see KH, look at this KH unit, pressure that is in the numerator up. That means here the concentration is in mole fraction only, that's why that concentration unit is not visible here. Concentration unit is not visible means, see, in the previous question there was molar, but here there is no such terms. That means it is in the mole fraction format only. We know that mole fraction has no unit. So this is along with the mole fraction, and this bar pressure unit is on the numerator. So you will be using the common form, a general form, that is PB is equal to KH into XB. KH into XB. Now XB you can expand, XB you can zoom it. What is PB? That is 0.987 bar, which is equal to KH in bar only. that is 76.48 into 1000. Now, what is XB? XB is equal to NB upon NA plus NB. NB upon NA plus NB. What is this Na? That is water. That is due to water. Nb, that is due to nitrogen. So that is N of N2 upon N of N2 plus N of water. This is the thing. This is the explanation for this thing. What is given in the bracket. So this is Na. Na is that of water and Nb is again number of moles of N2. Now, for easy calculation, since the concentration is very small, I can neglect this NB part. I can neglect this NB part. So the equation changes to, that is 76.48 into 1000 into Nn2 upon N of water. I have neglected that NB because as compared to this water, the 1 liter of water, this millimoles of NB can be neglected. Now you can find out NN2. NN2 is equal to, what is N of H2O? 1 liter of water. Last year we learned the number of moles present in 1 liter of water is 55.5. So I'm replacing that down portion by 55.55. 55.55. So Nn2 is equal to, Nn2 is equal to, that is the number of moles of N2. Number of moles of N2 is equal to what all things? This 0.987 into 55.55 upon 76.48 into 1000. So we have calculated the moles. Now to find out the millimoles, what you have to do? That is to be multiplied by 1000. So I am going for that. N of N2 is equal to, N of N2 is equal to 0.987 into 55.5 divided by 76.48 into 1000. This is the moles, number of moles of N2. So you'll be getting these many moles. And the question is for millimoles. For millimoles, you have to multiply this by 1000. So what you will be getting, that is 0.716 millimoles, M moles. M moles means millimoles. First you find out the number of moles of N2, then you multiply that with 1000, you will be getting the millimoles. Now we are moving to the calculations of Raoults law. Heading is vapor pressure of liquid solutions. Vapor pressure of liquid solutions. Number one, liquid in liquid. Liquids in liquid. Number two, solids in liquids. Solids means here in your syllabus it is non-volatile solid, non-volatile solid in a volatile liquid. In a volatile liquid. So first we are going to that liquid in liquid, which accounts for the Raoults law. Which accounts for the Raoults law. Raoults. Raoults law. In liquid means I mix two liquids. In that case, we'll be talking about Raoults law. A closed vessel, in that one liquid is there, another liquid is there, a mixture of two volatile liquids. It is a closed vessel. So, vapors of that red is there, and vapors of that black is also there. Total pressure, we call it as total pressure of the gases above the mixture, that is PT. The partial pressure of red one, that is PA, in this vapor phase, mixture of this vapor. And partial pressure of component B is PB. So PA and PB. In the solution XA, there is a mole fraction of component A, and in the solution XB, the same vessel I am keeping here also, same size, same thing. One more vessel I am keeping, same size vessel, same size vessel. Now in this first vessel, In the first vessel, I have taken only one component. When the component A is alone kept in the first vessel, all the three vessels are of same size. And in the second vessel, I have kept only that second liquid. Above the first, there is vapor pressure due to the first liquid. Above the second, there is vapor pressure due to the second liquid. So here this is pure vapor pressure of the pure solvent A. Now here is only one component. So I am writing its vapor pressure at equilibrium as P naught A. P naught A. And here, that is with black, it is P naught B, means pure component. P naught B. So according to Raoults law, PA is equal to PA is proportional to XA. So PA is equal to P naught A XA. What is P naught A? When the pure component A is present in the same vessel. At equilibrium, what is the vapor pressure of the pure component A? Similarly, PB is proportional to XB, or PB is equal to P naught B XB. P naught B XB. So this is Raoults law. PA is equal to P naught A XA. PB is equal to P naught B XB. Now we know that PT is equal to according to Dalton's law, PT is equal to PA plus PB. That last year we learnt. That is, PT is equal to PA plus PB. That is according to Dalton's law, last year's. PT is equal to PA plus PB. Now, one more thing we can say, that is YA and YB. What is YA and YB? YA is the mole fraction of component A in the vapor phase, and YB is the mole fraction of component B in the vapor phase. So PA is equal to, one more thing I can write, PA is equal to, here on the top I'll be writing, PA is equal to YA P total. That last year we learned. Similarly, PB is equal to YB P total. So many equations are there in this. That is, PA is equal to P naught AXA. PB is equal to P naught BXB. PA is equal to P naught AXA. PB is equal to P naught BXB. Then PB is equal to this P naught BXB according to Raoults law. PA is equal to P naught AXA according to Raoults law. Then PA is equal to YA P total. This last year we learnt. Means in vapor phase, PA is equal to YA P total. Similarly, PB is equal to YB P total last year. Then according to Dalton's law, PT is equal to PA plus PB. What is P naught A? That is due to pure solvent A. P naught B, pure solvent due to pure solvent B. So these many equations we have learnt. This is 1, 2, 3, 4, 5. So 5 equations. This is 1, P is equal to P naught A X A, PB is equal to P naught B X B according to Raoults law. Now you consider, suppose this black one is highly volatile, that it exists only in the vapor phase. The black ones are highly volatile, that it exists only on the vapor phase. Now what happens? One liquid and the other gas. So it becomes what? Henry's law. Raoults law becomes a special case of Henry's law. Raoults law becomes Henry's law that time. Once again, consider this black ones are highly volatile, that it exists only in the vapor phase. So consider that this red one is only in the liquid phase. So that time this Raoults law becomes Henry's law. Okay, I'm stopping here. We'll continue in the next class. Thank you.